cannot get it, then he can later use recording. So no. Okay, I think in last class we were discussing about filtration, as far as I remember, right? So filtration is a process in which we separate solids from liquid. This is physical process. I think we have discussed already about filtration. We discussed about there are two type filtration, rapid filtration and zero sand filtration. Also, I talk about a little bit pre-cold filtration as well. And we discuss about differences in zero sand filtration and rapid sand filtration. Zero sand filtration में we discuss के filtration rate is the most important factor. Based on that, we decide whether it is rapid or slow. So filtration rate is within 5 to 515 meter per hour. And actually, this is meter cube per meter square hour. Filtration is within this range, then we call it rapid filter. Otherwise, we call it slow sand filter, particularly if filtration rate is 0.05 to 0.2 meter per hour. The main difference is filtration rate, which distinguish what type of filtration is this. And this filtration rate occurs because of the diameter of media. If diameter is media is large enough, 0.3 to 0.45 millimeter, then actually smaller, then we call it slow sand filter, or we use this kind of media in slow sand filter. If diameter is of media is 0.5 to 1.2 millimeter, means bigger, then we can use them in, or usually we use them in rapid filtration. That is the main thing. The other thing is the depth of filtration. So in rapid sand filter, we can go more deep, up to 1.8 meter. Another important difference is backwashing. So we do cleaning using backwashing in rapid sand filtration, whereas we do scraping in a slow sand filter for regeneration, or when we want to reuse for filtration the media. And we have discussed this thing already. We also discussed that we use sometimes different medias in one filtration bed. So we can say, like, if we use sand or anthracite, it is dual media filtration. This is the basic configuration we discussed about during filtration. We have filter media here. This is filter media. Filter media is placed on graded gravel. So this is graded gravel. Here you can see a layer of graded gravel here, which is sitting on under drain blocks. So these are under drain blocks, and this is the media. And you see here, over here is wash unit, and water goes through this media and then goes out. So this is basic structure. Here you can see something we call it wash troughs. So when we don't have we have to, when we operate it, water goes downward, and when we want to backwash, water goes upward and goes into this tray, and from this tray this goes out. So this goes out from here. It's there, no, not here, there. We also discussed about different configuration of a filtration. Conventionally, we use a filtration after sedimentation and coagulation and flocculation. So first step is coagulation. We add chemical and we let particles settle down or make a big flock, and then let them settle down here. And then whatever remaining on the subordinate end, particles are filtered out. So this is the conventional filtration system. When this water quality which is coming in has high quantity of turbidity or high value of turbidity, and it's variable. In this case, we use this kind of scheme or configuration. This is conventional filtration. But if raw water turbidity is less than 15 NTU, then we don't need to use sedimentation. Just we do for coagulation, flocculation, and then direct filtration. In this case, we don't need this sedimentation process. We call it direct filtration. If raw water is more clean, less than 10 NTU, then we just do coagulation. Even we don't need flocculation because already particles are very low. So we just use filtration. If raw water turbidity is within less than 10 NTUs, sometimes we use two filters. One is roughing filter to remove some part, and then filtration with different media. So we can use in two steps to remove all turbidity of particles. As I mentioned to you, that we can classify filtration based on one media or two media or three media. So monomedia, dual media, and trimedia. Sometimes we have deep monomedias also. If depth is very high, like 1.8 up to 1.8 meter. When we operate, when we start operation, there is a filtration filter and there is a media. When we start operation, and if you measure the turbidity in effluent and influent here and here, then you will see initially turbidity here, effluent will increase, increase, and then with time it will decrease and decrease to a minimum value, and this minimum value will continue for some time. After then, this media becomes saturated with particles. So whatever goes in actually begin to come out. Then we see the increase in turbidity in effluent. So the initial time when it increase and decrease, we call it ripening. And then filtration, when the turbidity of effluent is minimum, that time is called effective filtration. And we again begin to increase, then we call it, that time is breakthrough. So this time is breakthrough time. So we can keep an eye on effluent turbidity, and then we can decide, okay, this time is wash. When the turbidity is beginning to increase, then we have to wash, or we have to do backwashing of the filtration to clean it up. This is one way. The seeing turbidity and effluent quality. Another method. Let me clean. Another method of operation, or another way of, or another strategy to operate, is to see the available head, or what is the head loss. So when we have a filter is filled with media, so this is media, and you apply water on it. This is water, and if you see pressure here and pressure here, so the difference in pressure is, we call it head loss. The pressure difference is head loss between these two values. So when you start, when the media is clean and you start filtration, there will be not much difference between these two pressures, or we call it head loss is minimum. So we will have an clean bed head loss is very low value. And if water is clean, if this water is clean, then we can have only this value. There will be no head loss. I mean, there will be head loss some minimum, but not increasing. But if water is not clean, then particle will accumulate here. Then you will see increase in head loss. Increase in head loss means this difference, pressure here and pressure here will be different, too much different, and it will increase. So you will see the increase in head loss, which will reach a value when you will not have any place to to keep the water or any means let me draw. So when you when you start, this is filtration and this is media. When you start filtration, water will begin to accumulate on it because of the clogging of filter, and will reach a value in what you cannot keep it. Water will overflow. Means you will reach the maximum value or available head, the value of available head. You have to run at that time. You have to then backwash the filtration or the media. So either you see the quality of effluent or you see the head loss increase. Then decide when to wash. In case of zero sand filter, we don't backwash. In slow sand filter, the particle accumulate on the top of the batch and form a layer. We call it Chamarstuck layer. Chamarstuck layer. This is scientist's name. He just did some investigation on this layer, and he found that this layer has not only particle but it has a microorganism living in here. So when water goes down, he observed that not only the turbidity is removed, but some organic contamination also removed from water. So this layer is important. So, but after some time, when you operate like 1 month or 2 months, then you cannot. You will see the head loss in or increase, or water level will increase, and you have to scrape it out, and put new layer on the top. So you can then regenerate the media. We also discussed about the differences in last class, where slow sand filter has some advantages and rapid sand filters has some advantages. The slow sand filter is simple. You don't have to add any coagulation, low energy. You can adopt easily, great adaptability. You can build easily and install easily, and costs are low. So it's very simple method. In many rural area, the slow sand filter is more common because easy to construct, easy to operate, easy to maintain, and less money, less cost as compared to rapid sand filter, which is a bit expensive. And I will come back again to that one. We discuss also about pre-coat filtration, which is not that relevant for water treatment, so I skip it now. I don't know. I discuss about filter media characteristic. The filter media characteristic is media we use in the filtration. The media characteristics are very important for filtration, especially the grain size. Means the size of the grain. What is the diameter of this grain of media? We find the grain size using sieve analysis. How many of you have heard about sieve analysis? You can raise your hand. I can see you. Sieve analysis, okay. Merad, Javed, have you heard about sieve analysis? No? Anjum? No?
सर एक्चुअली सारे म्यूट पे हैं ना, तो अभी बात नहीं कर रहे वो, तो उन्होंने बंद भी कर दिया वीडियो ना. तो सीव एनालिसिस आई थिंक जो हम डिफरेंट टाइप्स ऑफ सीव जो लगाते हैं, मे बी उनकी एनालिसिस हो ऑन द बेसिस ऑफ पोर्स जो हम पर स्क्वायर इंच लगाते हैं सर सीव बनाने के लिए ना.
सर सीव एनालिसिस ये होती है कि हमारे जो ग्रेन्स होते हैं ना, उनकी साइज के हिसाब से एक सीव होती है, उससे हम उनको शेक करते हैं, वो पार्टिकल्स उसमें हो जाते हैं. 4 mm की होती है, 19 mm की होती है. आई थिंक सिविल में ये हमने सीखा है.
On the basis of batch number, sir.
Yes, sir.
जी हाँ, batch number लगाते हैं.
All of you are right. But how come you become unmuted? I mute you.
Sir, actually, we have option. We have option, sir. We can unmute ourselves, sir.
Okay, you can do yourself.
Yes, sir.
Okay. Yes, you're right. That sieve analysis is kind of using different sieves like this. You can see one
Yes, sir.
series of sieve, one sieve and another sieve, with different mesh size, and this is the mesh size, and finally you can collect. And from you when we put the sample here, some particle remain on the top rim and
Supplement.
others pass, and here according to the size of sieve, and some remain here, another pass, and so on. So some portion stay here, some portion stay here, some stay here, some stay here. Then we can wait. We can make. We can measure the weight of this the sieve particle staying on the sieve and of that particular size, and we can find out the sizes of particles or distribution of sizes of particles. So we do sieve analysis. Uh, for sieve analysis, we use geometric means and geometric standard deviation. Geometric means and geometric standard deviation, they are different than normal mean and standard deviation, a little bit different. But the geometric means tell us the central tendency, what is the majority of particles are in the sample, and the standard deviation tell us how much other particles are varied from the mean, the standard means. So you have to go, you have to see the definition of these two terms, the geometric means and geometric standard deviation. So this is your homework. Okay, what is geometric means and what is geometric standard deviation? These are useful parameter. Geometric means tells the central tendency, and geometric standard deviation may tell us the variation. So you have to do this, huh? What is the definition of geometric means and geometric standard deviation? Another parameter which is related to the grain size is effective size, or we write it as capital E. Sometimes we write it ES, effective size. In effective size, we usually determine two things. We call it 10% percentile size. Another is 60 percentile size. The 10 percentile size, or D10, is actually the media grain diameter at which 10% of the media by weight is smaller. So you measure the media diameter in your sample. 10% of the diameter by weight are smaller. Another, I will explain later on. So another coefficient is uniformity coefficient. So it is just the ratio between D10 and D60. This is the ratio. The ratio of diameter of media with 60% by weight is smaller to the 10 percentile size. Actually, is the ratio between D60 to D10. So these two, effective size and uniformity coefficient, are important. As I mentioned to you, then when you do the sieve analysis, then every sieve will have retained some particle, and you can measure the weight of that particle, or then diameter, because the weight is known, and then also the size of mesh is known. So you actually know the diameter. You can get this kind of curve. The diameter will increase, and then you can see the 30% have this diameter, or 60% have this diameter, or 10% have this diameter. You can find out this information using sieve analysis. This is typical grain size distribution curve. Using the sieve analysis, which I mentioned to you earlier. So if you have the percentage passing and the grain size diameter, the 60% by weight are passing, which have this diameter, or 10% by weight or passing, which have this diameter. So you can find the D10 and D60, and the ratio of these two is called uniform coefficient, or UC. Sometimes U, sometimes UC. So this both effective size and uniform coefficient, they have some relationship with the geometric means and geometric standard deviation with using this equation. So if you know the geometric means and geometric standard deviation, you can find effective size. Also, uniformity coefficient has some relation with standard deviation, geometric standard deviation, SG. So if you know the geometric standard deviation, you can find uniformity coefficient and vice versa. So application of these two equations are given in your book example 11-1. So you have to solve this problem yourself. You have to see. Okay? This is application of these two relations. Any question? Anybody has any question? He or she can unmute and ask me now. Any question by anyone? No question, then I'll continue. So all of you have to solve this problem. Example 11-1. Another characteristic or property of media is hardness. So the media we use should be strong enough to withstand the pressure we apply during backwashing. Usually we use parameter or unit, we call it Mohs hardness number. So diamond has Mohs hardness number of 10, so which is very hard. So we have to see the hardness of particles, because the particles should withstand the pressure when we apply, especially when we apply backwashing. Another important parameter is porosity. The porosity means how much empty area is within the bag. So this is actually porosity of in-place media. So there are two types of porosity. One porosity is if there is a grain, the grain may have some porosity within it itself. But when you have many grains, so it's tell the porosity between these two grains and within the grain. So it is actually a combination in-place media porosity. We can find it using this formula. Here VV is volume of white and VT is total volume of media. So we can find the VV is VT minus VM. The VM here is volume of media. VT is total volume of media bed. So using this formula, we can calculate porosity, which is represented by epsilon. Of course, the media is more porous, the filtration rate will be higher. So porosity is important parameter. I don't know I discussed earlier in the graph or not. Maybe not. Anyway, it's related to the media diameter anyway. So media diameter is more, the porosity will be more. You can find this porosity using this equation. Another important characteristic is specific gravity. Because the specific gravity is important, because when you do backwashing, if you have two media, so say one media is like this and another media is like this. If you do backwashing, say this has higher specific gravity than this one, what will happen? This particle will go up during backwashing, and when you stop backwashing, the particle will settle down. So you must know the bottom particle which you want to keep in the bottom should have more specific gravity than the particle you want to keep on the surface. So specific gravity is important because it tells us after how it determines the arrangement of particles after backwashing even. These are some typical properties of a filter media. Like GAC has a 8.8 to 1 effective size, and uniformity coefficient is 1.3 to 2.4. Hardness is quite low. Porosity is 0.5. a specific gravity in 1.3 to 1.7, and this is sphericity is how much the media is round or sphere. So based on specific gravity, if you are using, say, this one and anthracite coal, so it is very difficult to separate them because the specific gravity is very similar. So when you will do backwashing, you will have mix of anthracite core and GAG. But if you are using GAG and garnet, the specific gravity is different. So if you are using two media, say one here is one media, say this is garnet, and here is GAG. And when you do the backwashing, then you will expect that after backwashing, this will be garnet because the specific gravity of garnet is 3.6 to 4.2, so it's quite heavy. So it will settle down on the bottom, and here specific gravity will be 1.3 to 1.7. It will be on the top. So based on a specific gravity, you can select your media for dual media filtration. The mechanism of filtration, the theoretical mechanism is based on different mechanism, including mechanical screening, means particles trap because of the size is bigger than the pore size or porosity, or sedimentation, just particles just come and just settle down in the media. The flocculation, the particles, two particles become big and then entrapped within the media, or one particle even is smaller, is because of some forces by media is just intercepted by media, or because of the velocity, particle just has some impact and stopped. So there are number of mechanisms involved in filtration, and it's quite difficult to do some modeling or prediction. It's difficult, although there are some models. One way of modeling is just you do model of individual mechanism. Another way of modeling is just you do model whatever happening in a bulk condition. So there are two type of model. So we call them fundamental model or microscopic level, which actually model actual transport and attachment mechanism. They're relatively complex, but anyway, it's very useful to evaluate different design. Another type of model are phenomenological or macroscopic model that's based on phenomena which attempt actually whatever happening in physically during the progression of the cycle. It tells us effective filtration and breakthrough some empirical parameter from some specific study. So generally, anyway, there are two type of filtration. One is microscopic, another is macroscopic. Microscopic see the individual transport or filtration mechanism, like individual mechanism, and then microscope see as a whole, all of them, whatever happening during physical filtration. So this model developed by Rajgopalan and Tian, this we call RT model, which talk about filtration depth and filtrate quality. You can see for different effective side and uniformity coefficient, they can have some different curves. So this model by Rajagopalan and RT can be used to predict for specific particles, what will be the quality of a filtrate at what depth. It can tell us. or it can be used in even for dual media or monomedia. Rajgopalan and TAN model is very popular to predict. We can also model the change in concentration of particle with depth. So if say Z is the depth, Z direction is depth, and the filtration happening is like this. So the concentration is the concentration of particles during filtration. The change of concentration of particle with change in the direction or with depth is directly proportional. Is actually is directly proportional with the concentration of particle itself. And when you can remove this proportional design, you can write a change of concentration and depth is actually, and we have to have negative sign because the concentration is decreasing. So we can have this negative sign here as well. Here. But this filtration coefficient has some function. I mean, is depending on both time and depth. The value of this lambda is actually not constant. It changes with time and depth. And also depend on filtration rate, grain size, and square of viscosity. So this constant has depending on many things. But anyway, this Rajgopalian model, which I did not show any equation, or if we just use this kind of macroscopic modeling with change of concentration of particles with time. If we make if we have a filtration and we just see small unit and make mass balance over this unit, we can write this equation. Here, this is change in mass accumulate per filter bed volume or filter bed volume, change in mass. So this is change in mass with time. Is directly proportional to change in concentration with depth. And then when we remove this proportional time, we can write here filtration rate. This filtration rate is as you know, meter cube per second per meter square of the surface area. Also, we can measure in meter per second. So this filtration is in meter per second. And we can combine both this equation and the previous equation here, and we can write this term change in mass, accumulated mass particle with time in terms of this one, lambda, filtration rate, and concentration. This is basic phenomenological model or macroscopic model. Anyway, there are these two models are quite complex, both Rajgopalian and this macroscopic model. So we will not discuss in detail this one. There are some simplified steady state model. When filtration occurring at steady state, then we can have this simple equation, these two simple equations. Which tell us the time to breakthrough and also the time to limiting edge. So we need to know these two things. So here we can, using this equation, we can find out the time to breakthrough and time to limiting edge. Where VA is a filtration rate, C naught is the initial concentration, CE is effluent concentration of particle, and D is depth of filtration bed, and the sigma B is specific deposit at breakthrough. There are some more hydraulics equation involved, and particularly Carmen-Cozzini equation. This equation tells us about head loss in the filtration of uniform particle when Reynolds number is less than 6, or another equation which tells us head loss of different size of particle, where This related is related to here is fraction factor, and Reynolds number can be determined by this using this. This equation, the Karman-Cousine equation, is derived from Darcy-Weisbach equation. Means that Darcy-Weisbach equation talk about flow in closed conduit. Means if you have a pipe, and then you can using this equation you can find the head loss in the pipe. So let me share something more. Okay, so when we have filtration, so we have grain size, different grains, and we have a pipe. So Darcy-Weisbach equation talk about a flow in pipe in a closed conduit, and that consider that there are different pipes in one pipe. This situation is similar in filtration. If you see here, water flowing from downward, water is passing through kind of pipe. This wide actually become pipe, or say this become pipe. This become pipe. So is this situation is very similar to the situation where the combination of closed conduits. So we can apply the same equation, which is derived by Darcy-Weisbach equation, and this equation is similar to Darcy-Weisbach. Karman-Cousine later developed. We can use this equation for filtration bed or bed used for filtration bed composed of same size of grain or same diameter of grain, or this one if the diameter of grain is different. In this case, then we have to use the friction factor, which is based on porosity and Reynolds number, and we can find the Reynolds number using this equation, which says particle shape, the factor, diameter of particle, filtration velocity or filtration rate, density, and viscosity. There are some more equations when Reynolds number is not so low or more than 6, then we can use this equation developed by Fair and Head, or another very famous equation, Argon equation, when Reynolds number is more than 6 or higher than 6. So if Reynolds number is lower than 6, we use this equation, which is Karman-Cousine equation. And if Reynolds number is more than 6, then we use this equation, Argon equation. This very similar to this equation which I mentioned to you earlier. This one, Karman-Cousine. Similar equation which is very common is Rose, developed by Rose in 1945. It is for calculation of head loss through a clean stratified sand filter with uniform porosity. Given here. So if you can see here, the head loss is related to approach velocity, also known as filtration rate. This one, depth of filter sand or sand filter, shape factor, acceleration due to gravity is a constant, porosity, geometric mean diameter of sand, drag coefficient, and friction, mass fraction of sand. So if you consider this thing, the depth is say constant, shape factor is constant, G is constant, porosity is constant, friction factor is constant, drag coefficient is constant. So hydraulic rate is directly proportional to, in these cases, is filtration rate. So you can change the filtration rate, increase filtration rate, then friction factor will increase. Also, the hydraulic load will be increased. Do you understand? Anyone has any question? This equation, about this equation. Are you following whatever I am talking? So we will use this equation for calculation of head loss. Here you can see here something, another summation sign. This summation sign actually account for stratification of sand grain size in the filter. Means that there are different sizes of grains, and we have to consider all of the sizes of grains. So we have to sum all of them. So we have to sum all of these terms when we calculate the head loss. This geometric mean diameter of the sand, which is dg, we can calculate using this equation. So if we do the sieve analysis, then we have one sieve up and one sieve down. So say this one D1, this one is D2. Some particle will go down, some particle will stay here. And then you can have D1 and D2. So the particles stay here as D1. So particles stay on the first sieve is D1, particles stay on the second sieve is D2. And then we can find the geometric means using this equation, geometric mean size of two successive C's. And we can use this GG value here. So if you see this equation, the head loss is directly proportional to the square of filtration rate. As I mentioned to you, head loss is directly proportional to the square of the filtration rate. So filtration rate is higher, the head loss will be more higher. So if you increase the small increase in the filtration rate, you will see the more change in the hydraulic head loss. If you see also here this equation, head loss is also inversely proportional to the diameter of the grain. So head loss is inversely proportional to the diameter of grain. If you keep all other things constant, you can see head loss is inversely proportional to the grain size. It means that if you increase the grain size, the head loss will decrease. If you decrease the grain size, the head loss will increase. This is logical, right? Do you understand this point? So if you decrease the particle size, head loss will increase. If you increase the grain size, the head loss will decrease. And it is this logical also, right? Any question by anyone? Okay. Another thing is the porosity. So porosity is a constant for bed, but consider this porosity power is 4. So if porosity is change in porosity will impact on head loss very much, and inversely it will impact also inversely. So head loss is also directly inversely proportional to porosity by the power of 4. So a small change in porosity will affect the head loss inversely. So if you increase the porosity little bit, you will see head loss decrease. If you decrease in porosity little bit, you will see a lot of head loss increase. These 3 things you have to understand using this equation. You can easily understand it. The head loss has a relation with the filtration rate. Of course, with the power 2. Head loss has some relation with the geometric diameter. Head loss has filtration as a relation with porosity, and it's too much strong. Okay, so let's solve one example. And this example is application of this equation which I just introduced to you. This one, this equation. This equation. I want all of you to answer me. Do you understand or not? I mean, I want to unmute you. I don't know how to unmute you. So anybody has any question can ask me now. Because this equation has some explanation of this equation. I will ask one question in exam or quiz. So it's important. So any question, please ask me. Otherwise, I will ask you. So Javed, you tell me. What will happen, Javed? Javed, can you hear me? I cannot hear you. How to unmute you? Javed. Yeah, Javed, can you hear me? Yeah, Javed.
Yes, sir.
I cannot hear you actually. So better you speak loudly, or maybe you can.
Yes, sir, I can hear you.
No, Javed, speak loudly.
Yes, sir.
Okay, Ehsan. Ehsan,
Yes, sir.
if we increase the porosity, what will
Yes,
happen
sir.
to head loss?
सर वो कम होगा सर, अगर हम रिलेशन के हिसाब से जाएं तो वो कम होगा सर, क्योंकि हमने जिस तरह पोरोसिटी की पढ़ा के पोरोसिटी जो है उसके हेड लॉस के साथ वो इनवर्सली प्रोपोर्शनल है सर, पावर ऑफ 4 के हिसाब से.
Power of 4, yeah, that's important. The power 4 is
Yes,
important.
sir.
So if
Yes, sir.
slightly increase in porosity will decrease head loss.
Yes, sir. Yes, sir.
Okay, very good. Tamattu Nisa,
जी सर.
if we change filtration rate, then what will happen to hydraulic loss?
Filtration rate.
If I increase the filtration rate, say I increase the filtration rate.
सर हेड लॉस इंक्रीज होगा. अगर हम इंक्रीज करेंगे तो
yeah,
सर वो
head loss is directly proportional with the power of 2 of filtration.
Yes, sir.
Yes, sir. जी, sir.
So let's solve this problem. The problem says that estimate the clean filter head loss in Ottawa Island proposed new sand filter using the sand described in example 11-1. The 11-1 I ask you to solve yourself, but that has some sand description. So they use the Ottawa Island use this sand which is described in 11-1. So we have to find what head loss and determine if it is reasonable. Use the following assumption, and we have to use the following assumption. This is the similar, I think, not similar example. Example started with 11-1. The loading rate is this much. This is actually what VA. Specific gravity is 2.65. The shape factor is 0.82. Shape factor is high. The bed porosity is 0.45. The temperature is 10 degrees centigrade, and the depth is 0.5 meters, which is D. So you have this information, and we have to calculate the head loss. So if you see this equation, we know the filtration rate, we know the diameter, we know the shape factor, we know the porosity, of course we know the G value.
सर काइंडली वो शो कर दें सर, स्लाइड जो है ना वो शो नहीं हो रही हमारे पास.
Okay, you cannot see. Okay, one way.
Yes, sir.
Okay. Can you see now?
Yes, sir. Now it's okay, sir. It's working now.
Okay. So in this, I will read again because maybe you can estimate the clean filter head loss in Ottawa Island proposed new sand filter using the sand described in example 11-1. So sand which is described in 11-1. Determine if it is reasonable using the following assumption. So head loading rate is given, which is VA. The specific gravity of sand is given. The shape factor is given, which is the shape factor. The bed porosity is given, which is epsilon. Temperature is 10 degrees centigrade, and depth of sand is 0.5 meter, which is D. So what we know from this equation is filtration rate. Filtration rate is known. Depth is known. Shape factor is known. G is known, and porosity is known. What we don't know, actually we know, we have to find diameters.
Yes, sir.
Because diameters is related to the previous example anyway, and the drag coefficient and friction factor. We have to work on this also. So the previous example, some information is given, like sieve analysis example, and these are the US sieve designation, and which is the opening millimeter. So it's 3 to and then 35 and 270. These are the numbers, and these numbers are related to these openings. So this sieve, if sieve number 3 has 6.33 millimeter opening, sieve number 35 has 0.5 millimeter, and so on. So this information is given in the previous example. This is a standard US sieve designation or sieve size. So in a previous example, they use sieve number 8 and 12, which retain 5.3%, as sieve number 12, and in between sieve number 12 and 16, 17.1% particles per retain, and so on. So this information is given. So if you see the sieve 8 and 12, sieve 8 and 12, then you can see in between 2.38 and 2. So the size which are actually in 10 are 2 millimeter. So we use here 2 millimeter, and we convert this 2 millimeter into meters. So that makes 0.002 meter. The C between 12 and 16. 12 and 16, if you see here, 12 is 1.68 and 16 is 1.19. So 12 and 16, they used number in between 12 and 16, this value, the 1.41. So they use about 0.00142. And see if 16 and 20, 16 is 1. So let me clear. 16 is 1.19 and 0.084. So they use 16 and 20, somewhere in between, in middle value. In between this middle value is 1. So they use 1 millimeter, that's 0.001, and so on. So you can then have these numbers using this this chart. Okay, so you have to make them. If 20 and 16 are given, then you may use the middle value. So you can have diameter of these within these seed numbers like this, and then you can also calculate for this diameter. You can calculate Reynolds number, because the Reynolds number. Sorry. Reynolds number, we can use this formula. So let's start for this particle, this diameter. So we have this diameter here. The shape factor is already given, which is this one, 0.82, and the filtration rate is also given, which is here. Now you have to consider here the filtration rate is given is 216 meter cube per day meter square. You have to convert into meter cube per second meter square, or meter cube per meter square second. So you have to convert this filtration rate into meter cube per meter square second or meter per second. So we just convert days into seconds. So we know this one, we know this one, we know this one. Because the temperature is given, so we can find the viscosity of water from the index, appendix of the books of your textbook. The 10 degrees centigrade, the viscosity is 1.307 10 to the minus 6 meters per second. So everything is known. We can find the Reynolds number. This is the Reynolds number here. So you change this diameter, you can find the Reynolds number, and another, and so on. So you have all of the Reynolds number here. When you find the Reynolds number, now you can find the drag coefficient. The drag coefficient can be found using this equation. Using this equation. Remember, we are talking about a flow in between the Reynolds number and laminar flow and turbulent flow in between. So we have to use this equation for calculation of Reynolds number. In the previous 6 lectures, I discussed about Reynolds number and drag coefficient relation. I think I remember. So for turbulent flow, you have different Reynolds number. For laminar flow, you have different Reynolds number. and respective drag coefficient in between turbulent and laminar, we can use this equation, which utilize Reynolds number to calculate drag coefficient. So because we know the Reynolds number, for example, for this one, we can just put here this one, and we can calculate this drag coefficient, which is in here. So for another Reynolds number, you can use same formula and put another drag coefficient and so on. Okay. So now we can sum this
drag coefficient, sir.
We can sum the drag coefficient term and diameter and the friction factor. The friction factor is fractional mass retained. Sorry, this is not friction factor. This is fractional mass retained. We can use we can find this number from here. So this is in percentage. Fraction mass retained. This is in percentage, and you have to convert into fraction. When you convert into fraction, you will have this number 0.053. So see here. So for first term for the here this one, drag coefficient is 9.689, friction factor F is 0.053, and diameter is 0.02, and we can have this term here is 256.64 per centimeter. Similarly, we can calculate different summation term here for all of the diameter and friction, which is retained within these seats. So we can sum all of them. Total sum will be here 75,025. Do you understand? I forgot. I just when I was talking about the drag the diameter, this diameter actually is calculated using this equation. So when you see the 8 and 12, so you have to use 8. This is 2.38, and then the 2, which is 12. 12 is 1.68. Sorry. .68.
Multiply 1.68.
0.68. That's the power 0.5.
0.5, sir.
Then you will get this number, and you have to use this one for all of them. So we got this number, which is 70 for this equation, which we didn't know. Other things are known, so we can just calculate head loss easily now. So head loss can be calculated with all terms, known terms. It's 0.76 meter. So this is the head loss when the particle size are different. Different particle size is stratified. They have different layers of particles in a sand filter. Any question till now? Any question? Any question? Ehsan, you tell me. Do you have a question? Do you understand
sir.
everything?
Yes,
Everybody
sir.
understand everything? Any problem? Anybody has any problem?
सर सारे ऑलमोस्ट म्यूट पे हैं सर, आप उनको अनम्यूट
No.
कर दें सर.
Okay.
No problem.
I will try to unmute all. Wait.
सर ये ऑप्शन है, आप जाएंगे ना सर पार्टिसिपेंट में, तो वहाँ पे आप अनम्यूट कर सकते हैं.
Yeah, yes, sir, I know. I have to see participant. Unmute all. Okay, all are unmuted now. So unmute.
Can you hear me, sir?
Yeah, I can hear you. Who are you?
Amir, sir.
आमिर सर.
Okay, I unmuted almost except Mera. Okay, I have I want to get your feedback. Do you understand? Do you get any problem, internet problem, anything you can discuss one by one? So tell your name and start saying anything. Anjum, you tell me any problem? Amir, do you have any problem?
Sir, with the lecture or with the time?
Anything?
No, sir. I don't have any problem, sir.
Javed, do you have any problem? Satesh, I see Satesh name only. Are you here, Satesh?
Yes, sir. I can hear you.
Do you have any problem?
No, sir.
Zohaib,
No, sir. No problem, sir.
I mean, I want to discuss the time of the class, or the way I am talking is okay or not, or anything. I need your suggestion.
No, sir. I'm agree. Time is.
Time is perfect.
No. Time is perfect, and I think there is some problem in the video
problem.
No, sir. I mean, sir, there is some problem in transmission, sir.
How?
In video transmitting, sir.
Actually, we can't hear.
Sometimes we listen.
There are lot of other
Sometimes
noise.
we
can't
listen.
hear.
Sometimes we not, sir.
That's just because of the internet.
So
Yes,
that is
sir.
I haven't found any
That's
problem,
why.
because I haven't found any problem during the lecture.
So this is your.
So no, I think, sir, this is this is the first day that's we observe. So inshallah, from tomorrow, it may not occur, sir.
Okay. Actually, I want to have this class not tomorrow, day after tomorrow. So tomorrow is Wednesday, and the day after tomorrow is Thursday. So we have class on Tuesday and Thursday, right?
Only, sir.
Yeah, Tuesday and Thursday, just like we used to do in our
Okay, sir.
regular semester. So how is your lockdown is going? You are enjoying your lockdown, or?
No, sir.
Of course,
sir.
Nobody
we are
enjoying here, sir.
Yes, sir. We are enjoying.
Yes, sir. We all are enjoying, sir.
You are staying
I
home,
don't
or
know
you go
about
out
others,
also?
but I'm enjoying.
Corona to end.
It's good chance for you people to eat new kind of food, or cook new kind of food, or
Of course, sir. E-learning, sir.
Also, anyway, I'm going to upload this slide through LMS.
Oh,
So
thank
all
you, sir.
of you
Thank
will
you.
have these slides, and I will continue on this lecture on filtration next class. I stop here now. Yeah, I want to see the quality of recording because this thing is recorded. So how many of you are not here? I think Ramsha is not there.
Yes, sir. Only Ramsha is not here.
And Safia, sir.
Safian is not here too.
Yes, sir.
And who else?
And I
Imran.
think, sir, Imran, sir. Yes, sir.
Imran is not here. Three are not here. Why they are not here?
I think Imran is. So he lives in the village, so that's why he may not access with the net.
Okay, I stop here. I will try to
Yes.
upload the recording also and share the link with you. And also I will
Okay, sir.
upload this slide to you so that you can follow. I hope that you enjoyed this lecture today.
A lot, sir, a lot.
So we will continue inshallah on Thursday 10:30. Okay.
Yes, sir. Yep.
Okay. Have a good day today.
Allah Hafiz, sir.
Thank you. Allah Hafiz, sir.
Allah Hafiz, sir.